Hi everyone, today I'm going to talk to you about dual carbon batteries, which are an innovative method of storing energy. But first, we need to understand how a battery works. Batteries work by converting electrical energy, which we use to power things, into chemical energy. And whilst electrical energy typically takes the form of an electron current moving around a circuit, chemical energy, at least in a battery, can be stored as ions. And when we talk about batteries, we use energy to refer to the total amount of work that can be done, and power to refer to how quickly that work is done. Think of it as the difference between how far a car can travel on a full tank versus how quickly it can accelerate. In more detail, a battery contains two electrodes, called a cathode and anode, which are connected by a wire that contains a load, for example, a light bulb or the phone that you're charging. In this diagram, we're looking at a lithium-ion battery, which is the most common type of battery in the world, and has a very high cell voltage and is also rechargeable, making it quite useful. One electrode in this battery is made up of a lithium metal oxide, whilst the other is made of graphite, which is based on carbon. Batteries also contain an electrolyte, which is made of two ions. And in this example, a lithium-ion battery has a positively charged lithium ions that are contained in the cathode to begin with, and negatively charged counter ions here shown in green. And the identity of this counter ion can vary. However, in the fully discharged state, all the lithium ions are contained within the cathode. As we begin charging the battery, some of these lithium ions move out from the cathode into the electrolyte. Later during the charging process, lithium ions move from the electrolyte into the anode, but others are still moving from the cathode to the electrolyte. So it's clear that lithium ions don't move all together. However, they do move through a process called intercalation, where they jump from electrode to electrolyte and back into another electrode. By the time the battery is fully charged, all of the lithium ions are now contained in the anode, but you'll notice that these green anions have not moved anywhere, so only one ion is doing the work. And therefore, as we discharge this battery, lithium ions will move back from the anode into the electrolyte and eventually into the cathode, liberating electrons that can power some application, for example, a light bulb. And because this process of charging and discharging simply involves one ion being shuttled between these three components, it's known as a rocking chair mechanism. Now, lithium-ion batteries are great and are very useful, but they do have a few issues. The first is that lithium is actually quite scarce on the Earth. The second is that the lithium cathode here uses a toxic metal oxide, which means that these batteries are not very environmentally friendly and cannot be recycled easily. Related to this is the fact that producing these electrodes takes a lot of energy, and therefore, whilst these batteries are commonly used because they're very useful, they're not the best for the environment. An additional issue is that there's an inactive ion, which means that we're losing the opportunity to harness and store more energy in our battery. So a potential solution to this is called a dual carbon battery, shown here on the left in comparison to our lithium-ion battery shown on the right. In a dual carbon battery, we replace this toxic cathode with another graphite, hence another graphite electrode, hence it's called a dual carbon battery. And instead of having just one ion do the work, we have two ions do the work. We still use lithium, and now our anion is called PF6, and instead it goes in the opposite direction to lithium, so it intercalates into the cathode. And because dual carbon batteries have both ions moving, they have a higher voltage in their cell and theoretically should contain more energy. So what did our results tell us about dual carbon batteries? Well, actually, we found that dual carbon batteries had a lower energy density and power density than lithium-ion batteries, which was a bit unexpected. So even though they have two ions that do the work, it appears that they don't contain as much energy and cannot release it as quickly. And this could be explained by the relative size of the anion that's being used. However, they still can be useful, and that's because dual carbon batteries are much more sustainable to create because they don't require any toxic metal oxides, and that also means they can be recycled more easily. Finally, they have a very good cyclic stability, which means that they can be used for a few years before they need to be replaced. This makes them ideal for use in the electricity grid, where we can make batteries as big as we need them, and therefore density of the battery is not a limiting factor. And so whilst dual carbon batteries might not be the next battery in your Tesla car, they could revolutionize the electricity grid. I'd finally like to thank Associate Professor Alexei Glishenkov and Dr. Srinath Reddy Ramareddy for their support in this project.